Hello everyone. Today we will be presenting a project titled LLM Performance Comparison in a Healthcare App. Our team includes Adhil, Arnav, Atharv, and Surya. This is the agenda for our today's presentation, which includes problem statement, objective, tech stack about the models, and results and future enhancements. This is the brief overview of our project. Our project evaluates how different LLMs perform in a healthcare application. The goal is to assess the trade-off between the cloud-based and local LLMs in the terms of their accuracy, cost, and various other things. This is the motivation of project, as this graph shows that many people self-diagnose through the internet, which can be harmful. So we have created an app which delivers quickly and which assess the reliable symptoms and give you medical insights about that. So this is a problem statement. So basically, LLMs have been truly comparable in a healthcare. Cloud models raise privacy concerns, while local ones need heavy resources. So we need a clear framework to evaluate them based on their speed, accuracy, and efficiency. Coming to objective, we have developed an interactive app to compare cloud LLMs and as well as local LLMs. The goal is to measure the performance matrices and response time. So this is the tech stack we have used. At the backend, we have used Fast API, and for the API integration, we have used Express as the major framework. Coming to frontend, we have used the React Native for the UI and Tailwind CSS for styling it. The database used is MongoDB, and these are the cloud and local LLMs. For visualization, we have used libraries of Python such as Matplotlib and Seaborn. So coming to the app, our app named is Health AI. So basically, the idea is simple. You have to enter your symptoms and different uh, parameters such as age, gender, height, weight, which will provide a brief response to your query. For our project, we have created various UML diagrams, which are as follows. The first is the use case diagram. Second is the sequence diagram, the state diagram and the activity diagram, and the ER diagram. So coming to the comparative study of our LLMs, we noticed that so basically we evaluated models like GPT-4, BioGPT, and Llama, DeepSeek. So BioGPT specializes in the medical queries, while Llama is more general purpose but highly efficient. So basically, both our local models are unique in different perspectives.
So now we take a journey through our app. So this is our landing page. So as I clicked on that button, I hadn't signed up yet. So now I'll start with the sign up procedure. I'll enter my email, studio05 at the rate gmail.com. I'll set the password as ABC123, the same as ABC123. So I've successfully entered. And now I'll enter my details. So gender male, age, I'll put my real age 19, I'll enter my weight, that is 67. My height is around 172 centimeters. Uh, 172. And then the symptoms. For the symptoms, I'll take simple symptoms such as cough and cold. Last, what do I do? I'll start out with asking this question to Gemini. So I'll create chat. So as you see, Gemini has successfully created a solution talking about brief assessment of health metrics and then steps to be taken, advice. Now I'll ask a question to Llama just to test one of our cloud and then one of our local models. So to test Llama, I'll just ask um, how many glasses of water should I drink? Use, So as you see, the answer is being analyzed, and the other answer. So the amount of water you should drink, blah blah blah. So the answer that it has generated, I think it's good. So this was the answer that was generated by our local model. And then to check out your previous chats, you just go to your chats and check it out, and then continue chatting with different models. And the sort of a secret sauce of our app is that whenever you try changing your model, the chat will hold context every time. So you may not have to create a new chat every time you want to chat with a new model. So that's it.
So coming to the LLMs part, we used several models like cloud-based models like Gemini, ChatGPT, and Claude, and local models like BioGPT and Llama. So BioGPT is a pre-trained model. It's pre-trained on 15 million PubMed abstracts, generates research-style responses. As it is its unique format, it scored 0 on rogue and blue matrices, but it still excels in speed and domain-specific knowledge. So this is the performance graph, timeline graph on BioGPT. Now coming to Llama, we used Llama 3.2 1B instruct sourced from Hugging Face, which is fine-tuned by PubMed QA dataset as shown in the figure. So this is the PubMed Q dataset. So our total fine-tuned code is available in the repo. So now coming in terms of matrices, coming to rogue score. BioGPT scores low due to format mismatch as the BioGPT accepts only research based. So we cannot compare to the normal questions as Llama. Coming to inference speed and memory usage, these are the graphs. Same, the blue score is also same. It doesn't have the format. It's the blue score is basically the quality generated. So the BioGPT doesn't give as it's a research based. It's the perplexity. The perplexity is the confidence in the model. Means how surprised the model by the actual next word in the sequence. It's the response time. BioGPT is fast and the Llama is quite slow as our Llama takes more RAM. Coming to cloud-based models, ChatGPT 4 leads in quality while Gemini responds the quick set. Access to these models can be limited due to token requirements.
So our app is built to allow users to query multiple LLMs for healthcare assistance. We integrated both cloud APIs like OpenAI, Gemini, and Claude via a fast API backend and local models using Hugging Face transformers. To optimize performance, requests were handled asynchronously with significantly improved response times, especially when querying multiple models at once. So steps for model integration. The backend was set up with fast API to handle model requests. For cloud APIs, we ensured structured and consistent request response formatting. On the local side, we used TorchServe and ONNX to boost performance, along with quantization techniques to reduce memory usage. On the front end, React Native allowed us to give users a clean UI where they could choose models and track responses in real time. All test results like latency, accuracy were stored in databases like PostgreSQL and MongoDB for data analysis. Other key challenges, one major challenge was latency with cloud APIs, especially on unstable networks. To solve that, we cached frequent queries, local models. On the other hand, we used too much memory, so we applied quantization and even model distillation. We also saw accuracy differences. Cloud models handled medical terms better than local ones, so we used prompt engineering and fine-tuned local models with domain-specific datasets. The learnings, we discovered that both cloud and local models have trade-offs. Cloud APIs are faster and more accurate, but rely on the internet. Local models offer privacy and offline access, but need heavy optimization. Techniques like caching, quantization, and asynchronous processing were crucial. Lastly, benchmarking in real-world environments like mobile laptops and VMs gave us deeper insights that we couldn't get from controlled settings alone. So moving forward, we want to improve benchmarking tools and analytics with automated testing pipelines and interactive dashboards. We plan to add more models like Mistral, Cohere, and Meta AI for a broader comparison. Our app can also expand beyond healthcare into domains like finance and law. To boost local performance, we'll fine-tune newer models like Llama 3.1 and test efficient models like Mistral on edge devices. We also aim to deploy a full-stack web app for wider access. In summary, cloud-based LLMs are ideal for speed and accuracy, but come with network dependency. Local models offer data privacy and offline access, but need smarter optimization to be viable. Device-level performance differences show why adaptive tuning is necessary. Together, these insights can guide AI deployment in healthcare and beyond. Thank you.